Einstein's Relativity, the Special Theory and the General Theory. Chapter 6. Edition of Velocities in Classical Mechanics. New Modern Translation 2025. Albert Einstein and Harry Yoon, Translator. Introduction, Chapter 6. Let's suppose that while standing on a firm ground, you can shoot an arrow at a certain initial speed, say, at 100 meters per second. Now, if you are riding a horse and shoot an arrow in the direction of the horse's movement, then the arrow will travel faster, that is, when the speed is measured with respect to the ground. On the other hand, if you shoot an arrow in the backward direction while on horseback, then the arrow will fly more slowly, again relative to the ground, because the horse's motion in the opposite direction will end up reducing the effective speed of the arrow. This is a well-known phenomenon that we should be all familiar with. Even a little kid knows that they can throw a ball farther, which depends on the initial speed of the ball, by throwing it while running forward. The faster you move forward, the farther you can throw a ball, with all other conditions equal. It's very likely that this has been known for thousands of years, since the dawn of civilizations. The rise and fall of civilizations, with some wild speculations, may also have depended on this knowledge since bows and arrows, spears, and other throwable weapons had been invented. The first person who understood the physics of this phenomenon at the quantitative level, however, was again Galileo Galilei, who Einstein called the father of modern physics. This is the topic of the current chapter, Chapter 6, edition of Velocities in Classical Mechanics, from the book, Einstein's Relativity, the Special Theory and the General Theory, New Modern Translation 2025. Modern physics as a quantitative science started at the beginning of the scientific revolution, by the people like Kepler and Galileo, among many others. Galileo, who was both the first theoretical physicist and the first experimental physicist in the modern terminology, was also one of the first scientists who recognized the importance of mathematics in physics, whose tradition really goes as far back as the time of Pythagoras and Plato. Galileo famously stated the following: "The book of nature is written in the language of mathematics." But the mathematics at the time really meant Euclidean geometry, that is, Euclid's elements, and some later developments by Hellenistic Greek philosophers like Archimedes and Apollonius. It was before the invention of calculus, by Newton and Leibniz, and analytic geometry, by Fermat and Descartes, etc. Galileo discovered so much about nature, with or without using math, especially in the areas of celestial and terrestrial mechanics, which were considered two separate subjects at the time. Aristotelian physics had been around for almost 2,000 years. Why didn't other people for 2 millennia discover some of these, almost trivial at least in hindsight, facts about nature? So, what made Galileo different? What made him special? As we briefly mentioned in the previous few chapters, Galileo was a rebel, regardless of whether he intended to be one or not. He started his career as a lecturer for mathematics and physics, after dropping out of medical school. But he was not very popular among the fellow faculty members. Nor was he well recognized by the university authorities. For one thing, he was rather critical of Aristotelian physics. Understandably, his career went nowhere. It was only after he published his first book, The Starry Messenger, that Galileo was able to secure his first permanent position as a professor. Richard Feynman stated, "There is no harm in doubt and skepticism, for it is through these that new discoveries are made." Galileo, as well as Einstein some 300 years later, was the embodiment of doubt and skepticism. He never accepted the dogmas of Aristotle at their face values. He had to think over and over, and test and verify everything. Chapter 6. Edition of Velocities in Classical Mechanics. Suppose that our favorite train with passenger cars is once again traveling on a straight and horizontal track with a constant speed, say, v meters per second, with respect to the railroad embankment or the ground. The speed can be measured in any different units, but we will use meters per second for concreteness. Suppose further that there is a man inside a long passenger car of the moving train, and that this man is walking along the length of the car, or more specifically in the forward direction of the train's movement. Let us denote the speed of his walking motion as w meters per second when it is measured relative to the body of the train, or the frame of reference which is stationary with respect to the train. Now the question is, how fast then, or at what speed, capital W, again in meters per second, does the man move forward when his motion of walking inside the passenger car is now viewed by an observer on the railroad embankment? The answer to this question seems to be straightforward based on the following considerations. First, if the man were to stand still for 1 second in the car, he would automatically move forward relative to the embankment by a distance, v meters, since the car itself is moving, which is numerically equal to the speed of the train, v meters per second. In addition, in that same 1 second, he moves forward by a distance, w meters, relative to the train, and therefore also relative to the railroad embankment, which is again numerically equal to the speed of his walking, w meters per second. Thus, in that 1 second period under consideration, he ends up covering the total distance, capital W, in meters. Capital W equals V plus W. When viewed from and measured with respect to the railroad embankment. In effect, therefore, the speed of his walking relative to the embankment is capital W meters per second. That is, capital W meters per 1 second equals capital W meter per second. This result expresses the addition theorem of speeds, or more generally, that of addition of velocities, as vectors, according to the classical mechanics of Galileo and Newton. This theorem implies that, among other things, the speeds of two combined motions in the same direction are simply additive. Later, we will see that the consideration that led to this result cannot be maintained beyond classical mechanics, and the above formula, therefore, is not completely accurate in reality. For the time being, however, and in particular in the next chapter, we will tentatively rely on this formula, assuming that it is correct. The translator's notes. Motions are relative, as all readers of this book must know by heart at this point. The motion of a body A can be described relative to another body B, or an inertial frame of reference. The motion of the body B can also be described with respect to yet another body, C. Now the question is, how do you describe the motion of the body A relative to the body C based on the descriptions of the two known motions, that of A relative to B and that of B relative to C? In the example of the introduction, the body A corresponds to an arrow, B corresponds to the horse or the archer on horseback, and C corresponds to the ground. In Einstein's example in this chapter, the bodies A, B, and C correspond to the man in the passenger car, the car or the train, and the railroad embankment, respectively. A quick summary. In classical mechanics, the speeds in the same direction are simply additive, and in general, velocities in different directions are additive as vectors. A velocity is a vector with a magnitude and a direction. For example, if a man walks forward at a constant speed w on a train that is moving at a constant speed v relative to the ground, then his relative speed, capital W when viewed from the ground, is capital W equals V plus W. Physical quantities. If you are new to physics, one of the most important concepts to learn is that we deal with physical quantities in physics. We do not just manipulate numbers. A physical quantity is a number plus a dimension. For example, a distance 500 meters is a physical quantity with an associated dimension, distance. Likewise, a speed, 100 miles per hour, is a physical quantity whose dimension is distance over time. Units are somewhat arbitrary, but they have to be consistent with the dimensions of the relevant physical quantities. For instance, we can use kilometers or miles or yards with a physical value whose dimension is distance. One thing to note is that when we use a variable or a constant to denote a physical quantity, the variable constant includes the dimension and unit as well. This is pretty much a universal convention in physics. As an example, when someone says that the maximum speed of his car, v, is close to the speed of light, c, the symbols v and c contain the relevant units as well. For instance, v can be 200 km per second, whereas c is, by definition, 299,792,458 meters per second, and not just a number. Hence, the dimensions of v and c are both distance over time. However, we made an exception in the translation of this chapter. The variables used in the main chapter, e.g., v, w, and capital W, all just represent pure numbers. Instead, v meter per second, etc., combined with the appropriate units, are physical quantities. The reason was, in his arguments in this chapter, Einstein was making numerical comparisons between physical quantities with different dimensions, e.g., distance versus speed. And we thought that this explanation was more clearly expressed if we use the more explicit formats, value plus unit, rather than physical value. We hope that this somewhat unusual notation will not confuse too many of the readers who are more accustomed to the normal convention of physics. What is speed? As probably every reader knows or should know, speed is a physical quantity that represents a distance traveled over a certain unit time period. For example, if you ran 10 kilometers in 2 hours, your speed was 5 kilometers per hour. Or, 5 kilometers per hour equals 10 kilometers per 2 hours. Note that we always include the units, and hence dimensions, in the calculation of physical quantities, at least in our head. This kind of speed is called the average speed in physics. You might have run sometimes a bit faster and sometimes a bit slower during that 2-hour period, but on average, you ended up running 10 kilometers, and hence your average speed was 5 kilometers per hour. The average speed is therefore defined as average speed equals total distance over elapsed time. Equation 6.1. Note that as Einstein relies on in his explanations in this chapter, the average speed and the distance are numerically equal if the denominator, the time duration, happens to be 1 in the particular unit used. For instance, if one walks 3.8 kilometers in 1 hour, his or her speed is 3.8 kilometers per hour. And if a beam of light travels a distance of 299,792,458 meters in 1 second, then the speed of this light beam is 299,792,458 meters per second. In fact, in classical mechanics, the distance covered by a moving body and the average speed of its motion are always proportional to each other within a given time period. For example, suppose that Alice, Bob, and Charlie go on a hiking for 4 hours. In that time period, Alice, Bob, and Charlie have hiked 16 kilometers, 24 kilometers, and 28 kilometers, respectively. Then, their average speeds are 4 kilometers per hour, 6 kilometers per hour, and 7 kilometers per hour, respectively. The distance ratio, 16 to 24 to 28, is exactly the same as the speed ratio, 4 to 6 to 7. One thing to note is that in the definition of equation 6.1, the average speed can take any values equal to or greater than 0, since there is no limit in the distance that a physical body can travel in a given time period in classical mechanics. That is, by definition, speed is 0 or positive and less than infinity. Now, a more interesting physical quantity is what we call instant speed. An instant speed is the value of an average speed when we take a limit of the elapsed time approaching 0 at a certain time t. What? You might ask. If the denominator of the above expression goes to 0, then wouldn't the whole value blow up? Well, no. As the elapsed time gets smaller, the total distance traveled during that time becomes smaller as well. Interestingly, as the time gets shorter and shorter, the value total distance over elapsed time eventually approaches a finite and stable value. This was first discovered by the ancient Greek philosopher, mathematician, and physicist Archimedes of Syracuse. This problem really originated from Zeno of Elea, whose notorious paradoxes puzzled many people for centuries. Aristotle was one of the first people who took the notion of infinity seriously, both infinitely big and infinitely small, often called infinitesimal. Ultimately, this idea gave birth to calculus in the 17th century at the time of Fermat, Newton, and Leibniz, as some of the readers may already be familiar with. Here's the definition of instant speed. Instant speed at t equals total distance traveled from t to t plus delta t, over elapsed time delta t, when delta t becomes infinitesimally small. As mentioned before, instant speed is a scalar quantity with only a magnitude, whereas the corresponding vector quantity, instant velocity, has both a magnitude and a direction, e.g. in the three-dimensional Euclidean space. Velocity in classical mechanics. Here's the definition of instant velocity at time t, vector v of t, using the vector notation. Vector v of t equals vector r at t plus delta t, minus vector r at t over delta t, when delta t becomes infinitesimally small, equation 6.2. Here, vector r of t represents the position vector, e.g. of a point mass at time t. If you are not familiar with vectors, then you can just treat a vector as a set of values. For example, in a two-dimension Euclidean space, vector r of t may be viewed as x of t, y of t in a certain xy Cartesian coordinate system, where x of t and y of t represent the x and y coordinates of the point mass in this system at time t. That is, equation 6.2 is more or less equivalent to the following two equations, again with respect to the given coordinate system. V sub x of t equals x at t plus delta t, minus x at t over delta t, when delta t becomes infinitesimally small. V sub y of t equals y at t plus delta t, minus y at t over delta t, when delta t becomes infinitesimally small. Where v sub x and v sub y represent x and y components of the two-dimensional vector, vector v, respectively. That is, vector v equals v sub x, v sub y in this Cartesian coordinate system. If you have some knowledge of calculus, equation 6.2 simply represents the fact that the instant velocity, vector v of t, is a derivative of the position, vector r, with respect to time. That is, vector v of t equals derivative of vector r of t with respect to t. Or using the same two-dimensional example, v sub x of t equals derivative of x of t with respect to t. V sub y of t equals derivative of y of t with respect to t, again in the particular coordinate system chosen. The instant speed and the instant velocity, e.g. of a moving body, at any given instant of time t, are related as follows, as we have stated a few times before. S of t equals length of vector v of t, equation 6.3. Where s of t denotes the instant speed at time t, and the operator, vertical bars, represents the norm or size of the given vector. For example, in our two-dimensional example, s of t equals square root of v sub x squared plus v sub y squared. Average speed versus average velocity. Average velocity over a finite time period can also be defined, for example, as follows. Vector v of t equals vector r at t plus delta t, minus vector r at t over delta t, equation 6.4. The only difference compared to equation 6.2 is that we do not take the limit of an infinitesimally small, delta t, in the case of average velocity. That is, it can be 2 seconds, or 5 days, etc. Now, average velocity is rarely used, if ever. When we simply say velocity in physics, it almost always refers to instant velocity. On the other hand, average speed can be still useful in many situations. Let's consider an example. Suppose that you leave your home, driving your car at 100 kilometers per hour instant speed, and maintain this exact speed throughout the trip. And you finally come back home after a certain amount of time has passed, say 4 hours. In this case, what would be your average speed for your entire trip? It is 100 kilometers per hour, regardless of how long you have driven, in fact. But now, what would be the average velocity of your trip? It is 0, since you have come back to the same location, your home. That is, the two position vectors, vector r at t plus delta t, and vector r at t, end up to be the same. Although we will not go into detail here, this difference has something to do with the fact that average speed is path-dependent, whereas average velocity is not. First, note that between the average speed and the average velocity of a motion, there is no equivalent relationship like equation 6.3. Average speed, equation 6.1, and average velocity, equation 6.4, are defined rather differently from each other. The total distance traveled is clearly path-dependent, even if we do not precisely define what this term means. On the other hand, the definition given above for average velocity, equation 6.4, depends only on two end values, vector r at t plus delta t, and vector r at t. We will deal with a similar situation later in the book, in particular, when we talk about the famous, or infamous, twin paradox. As a matter of fact, it is one of the fundamental and most interesting facts in physics, or in nature, that some physical quantities are path-dependent, broadly speaking, and some are not. Addition of velocities for mass particles. Let's go through Einstein's argument of this chapter again, and derive the rule of addition of velocities in classical mechanics, but in two dimensions this time. Suppose that there is a large ship that is cruising to the east at a constant speed, v kilometers per hour, relative to the surface of the sea, or the earth. Now, a puppy is running on the flat and horizontal deck of the ship in a certain direction with a constant speed w kilometers per hour relative to the deck. The direction of its uniform motion may be specified with an angle theta with respect to the direction of east, measured in the counterclockwise direction. In this situation, what would be the speed, capital W kilometers per hour, and the direction, phi, of the running puppy with respect to the surface of the sea and with respect to the east, respectively? Figure 6.1, a running puppy on a ship. If we follow Einstein's argument exactly, then we can make the following statements. For 1 hour, the ship moves v kilometers to the east. In that 1 hour period, the puppy moves w kilometers with respect to the ship. This motion can be divided into two components, one along the east direction, and the other perpendicular to the east, say, to the north. Using trigonometry, the east component of the motion is w cosine theta, and the north component is w sine theta. Then, in this 1 hour, the puppy has effectively run w cosine theta kilometers to the east, and w sine theta kilometers to the north. Now, with respect to the sea, earth, the puppy ends up covering effectively v plus w cosine theta kilometers along the east direction and w sine theta kilometers along the north direction. Combined together, using the Pythagorean theorem, the distance that the puppy covered in 1 hour with respect to the sea in kilometers is then capital W equals square root of v plus w cosine theta squared plus w sine theta squared equals square root of v squared plus 2v w cosine theta plus w squared. Where we have used the identity, cosine theta squared plus sine theta squared equals 1. Hence, the speed of the running puppy with reference to the sea is capital W kilometer per hour. Or square root of v squared plus 2v w cosine theta plus w squared kilometer per hour, equation 6.5. Note that when theta equals 0, cosine theta equals 1 and sine theta equals 0, that is, when the puppy runs along the same direction as the ship, this formula reduces to the one given in the chapter, namely, capital W equals v plus w, either viewed as a distance addition or as a speed addition. On the other hand, if the puppy runs in the opposite direction of the ship's motion, that is, theta equals pi, or 180 degrees, then this formula becomes capital W equals v minus w. Note also that in the limits, w much smaller than v, and w much bigger than v, capital W becomes v and w respectively, regardless of the value theta as they should be. The angle, phi, of the puppy's motion relative to the sea, measured with respect to the east direction, is phi equals arctangent of w sine theta over v plus w cosine theta, equation 6.6. In the limit, w much smaller than v, phi becomes 0, and in the limit w much bigger than v, phi approaches theta, both of which are rather intuitive. As before, classical mechanics puts no constraint on how fast the ship relative to the sea, and the puppy relative to the ship, can move. Hence, this two-dimensional formula for adding two velocities puts no constraint on the final combined speed, capital W. That is, capital W is 0 or positive, and less than infinity. Can we extend it beyond two motions? What about three motions? What about gazillion motions? Well, let's consider adding three motions for now. Suppose that there is a huge cruise ship, 1,000 times bigger than an aircraft carrier, which is traveling to the east, at a constant velocity relative to the sea. This cruise ship has a railroad on the deck, which runs straight at a certain angle with respect to the east, and a train is moving at a certain constant speed on this railroad. Inside the train, there is a man who is walking again with a certain fixed speed and direction relative to the train's motion. Now, what would be the speed and direction of this man relative to sea? The answer seems obvious in the one-dimensional case, that is, when all three motions are aligned to the east, since the speeds are simply additive. Do you agree? What happens if we consider this problem in the two-dimensional Euclidean space? Can you derive formulas for combining three speeds and directions in the two-dimensional case? Addition of velocities for waves. Let's consider an interesting variation of Galileo's velocity addition formula as something to think about. Instead of material bodies, what happens if we consider waves? But what does that even mean in the context of adding speeds, and in the context of mechanics? First of all, what is wave? This question will open a Pandora's box. Many readers who are new to physics may have noticed that the use of various terms in physics is rather sloppy, despite its reputation as an exact science. This is especially so with the word wave. Traditionally, wave meant the waves like sound waves or surface waves, e.g., ripples on a lake or the ocean waves that we see on the beach. This kind of waves were the only waves. They are now called mechanical waves. A mechanical wave is an oscillation of a medium. A sound wave is a three-dimensional, propagating oscillation of the air, both in space and time. A surface wave is a two-dimensional oscillation of an interface between two media, e.g., between air and water. This notion was deeply ingrained in our habit of thought for thousands of years. And that was why, when people started realizing the wave nature of light, in the beginning of the 19th century, they almost automatically assumed the existence of some kind of mechanical medium for propagating light. Anything else was most likely unthinkable. They called this matter ether, with changing definitions like chimera, as we briefly mentioned in the last chapter. It was again Einstein who first postulated that wave could propagate without medium. Just think about how radical this idea was. How can a wave propagate without a medium? Well, that's how it is viewed at this point. We simply changed the definition of wave. Light, an electromagnetic wave according to Maxwell's classical electrodynamics, propagates through vacuum or nothing. In 1924, Louis de Broglie proposed that matter particles such as electrons, or even you and me, were also waves, which became the basis of Schrödinger's wave mechanics. Then, Max Born suggested that the wave in the wave equation was not a matter wave, but a wave of probability, or probability amplitude more precisely. Now we use the phrase wave-particle duality to refer to this dual nature of matter and wave. In modern quantum field theory, elementary particles are considered some kind of excitations or waves of quantum fields for both matter fields, fermions, and force fields, gauge bosons. At this point, nobody really knows what the word wave means. In any case, loosely speaking, any wave can be viewed as some kind of periodic oscillations over time, with or without a carrier medium, which may or may not propagate in space. Hence, all waves have a speed, which can be zero, and a frequency of oscillations, among other things. We only consider here pure sinusoidal waves for simplicity. That is, each wave has only one frequency. Here are some of the important concepts related to mechanical waves, to the extent relevant to our discussion. First, the frequency of a mechanical wave, often denoted with FF, is the number of cycles of the oscillating medium for a unit time. In modern physics, angular frequency, omega, the number of radians per unit time, is more frequently used. That is, omega equals 2 pi f. Frequencies are most often measured in hertz, whereas angular frequencies are generally measured in radians per second, or simply 1/second. The period of an oscillation in time, often denoted with t, is the interval of time between the consecutive repetitions. Therefore, the period is simply the inverse of the frequency. T equals 1/f equals 2 pi over omega. Next, the wavelength, lambda, of a wave propagating through a medium is the distance over which the wave's shape repeats, measured respect to the medium. In case of a pure sinusoidal wave, it's the distance between two consecutive corresponding points of the same phase on the sine wave. Finally, the speed of a sinusoidal wave relative to the medium is the distance traveled by a given point on a wave in a unit interval of time. If we denote the speed of a wave as u, then u equals lambda over t equals lambda f equals lambda omega over 2 pi equals k omega, where k equals lambda over 2 pi is called its wave number. In general, a few different kinds of speed can be defined for a wave, such as phase velocity and group velocity, but we will not discuss them here. Now, let's go back to the original, sloppily stated question in the beginning of this section. This question can be more precisely formulated in a few different ways. Here's the easiest version, which can be expressed as follows, using a similar example as before. A cruise ship with a swimming pool on its deck is cruising to the east, as before, with a speed v relative to the sea. Now you create ripples on the surface of the water in the middle of the swimming pool, which propagates in all directions, e.g., a circular wave. Let's further suppose that the ripple wave has a wavelength lambda and a frequency f. The question is then, what is the speed of the ripple wave along the east, capital W sub e, and west, capital W sub w directions relative to the sea? We will leave this question as an exercise to the readers. Just think about it if you like. You don't have to use equations if you don't feel comfortable. Note that we are dealing with a one-dimensional case, that is, along the east and west directions, or the forward and backward directions relative to the motion of the ship, respectively. In Appendix D, we will discuss a little bit more difficult and a little bit more interesting problem, in which either the source or the observer of a mechanical wave, or both, is moving with respect to the wave medium. In this case, the wavelength and the frequency of a moving wave will appear different to the observer, whereas the speed of the wave, with respect to the medium, remains the same, compared to those values viewed from the stationary source. This is known as the Doppler effect, which many of the readers must be familiar with, or at least have heard about. What's next? In the next chapter, Chapter 7, Einstein describes the conflict between the Galilean principle of relativity and the new physics, Maxwell's electrodynamics, at the end of the 19th century that started it all. Chapter 7, The Law of Constant Speed of Light and the Principle of Relativity.